Yes.
Can we discuss one of the questions that was stuck in, like, if, so anytime after this or before the session, whenever you are.
Which questions?
So I have some issues with one of the questions in graph theory in PYQs.
PYQs. Okay. Yeah, we can have a separate session over PYQs. But after taking the doubts from practice assignment and activity, if we have time, then we can go over the PYQs too.
Okay.
That won't be an issue.
Madam, I have one clarification.
Yes, Nari.
See, actually, now the first 10 weekly graded assignments only are taken for grading.
Yeah, I think this is mentioned in your graded document, maybe.
Yes, it is mentioned, madam. So then in week 11, it has to, they have given some deadline and they told it will be, what exactly it is telling is that it will also be week 11, it says. You may submit any number of times, your details, final submission should be considered for grading. What is this grading means?
The assignment will be
Week 11, first line, second line, or whatever it is.
Oh, I think this is just what you can say default lines for all graded assignments. So they may have forgotten to remove this from week 11
Yeah, but
graded
I
assignment.
have checked up, almost all the courses are having first 10 weeks only are taken for grading. Previously, it used to be best 10 out of 12 actually.
Yeah. But in our
So,
course, only 11 weeks are there, so that's why we are taking best 10 out of 11 maybe.
no, it is not best 10 out of 11, madam. It
Yeah,
says
it's
first
first
10
10.
weeks,
First
first
10.
10.
Okay.
So that is something like it is not in line, no, madam. Like 11th week also we can try and we can get a better score in that. No? So what is the reason behind that? Actually, any idea you have?
Let me check with Vishal sir because I also don't know about the grading assignment what they have told.
It would be possible if you can take the best 10, it will be nice, madam. You can please put a word to the POD or whoever is in charge.
Yeah.
No, but for the interim exam, it should be from week 1 to week 11 only, right? Am I right?
For end-term exam, yes, week 1 to week 11.
Both the mathematics and statistics one.
I can't say about stats, but yes, for the end-term, basically the syllabus will be from week 1 to 11, but the weightage may differ. So that means there will be very few questions from week 1 to 5 or week 1 to 8. It depends course to course.
Okay.
I mean, another
But for math,
yeah, please.
but for maths, so what is the weightage like? From week 1 to week 5, week 5 to week 9.
Yeah, we'll describe the weightage in the revision session because I haven't given the weightage. So sir will give us the weightage and then we will discuss accordingly in the revision sessions. So that's why I told at least don't miss the revision session. Either you can watch the recording or you can join it over the live. Both things are okay, but at least go through the revision sessions at least once.
Okay,
I'll
sure.
just message sir about this best 10 class.
Okay. Sorry, Sandeep, you can go ahead.
Yeah, sure. Thanks. Yeah, can we discuss Bellman-Ford and Warshall algorithm at once in a bit, bit detail?
Yeah, sure.
With some of the examples. So yeah, and also the concept of minimum vertex cover.
Set of minimum vertex cover. Okay. Because my screen is not visible, no?
Yes, ma'am.
It's visible, ma'am.
Will week 11 S2.
Wait a minute. Is this visible? Whatever I am writing?
Yes, ma'am.
Yes, ma'am.
I have written week 11, right?
11 within double quotes.
Yeah, fine. So, what is a Bellman-Ford algorithm? So Bellman-Ford algorithm actually we will use to find out the answer for single source shortest path. So that means if you want to find out the shortest path from a fixed vertex to any other vertex, that is our single source shortest path problem. And for that, if we have negative edges, so we know that Descartes' algorithm is not able to deal with negative edges. Negative edges means those edges which has negative weights. So we cannot apply Descartes' algorithm over that. So what uh, they done, they some kind of modified Descartes' algorithm in such a way that we have to uh, recheck it. So that means we have to compute the shortest path at various steps using some idea that we will increase the number of edges, or we will track the distance, and then we arrive at one algorithm. It's known to be Bellman-Ford algorithm. Okay. So in Bellman-Ford algorithm, one keynote is here we have to compute the distance over the steps. So here, if the number of vertices in graph G is n, then we have to compute n distances, or n steps we need to do. Okay.
No, we need to do this n-1 iterations, right?
Yeah, so that means n steps will n-1 iteration. So if you starts with 0, na?
Okay.
Yeah, so then it will be n minus steps. But okay, yeah, the answer will, I think, gotten by n-1 steps, or n steps. In n step, you will get the repeated answer. So you will be sure that that particular graph, in that graph, the Bellman or the single source shortest path is well defined. Okay. So what we need to do, suppose we have a graph, so we need to find out several steps. So for that we maintain a table. So in that table, here we will have a set of vertices, and here we will have our steps. Okay. So in initial steps, suppose that your source vertex is 0. So what you will do, so this is your initial steps, or the 0th steps you can consider. So over this steps, we say that, okay, the distance of source vertex to itself is 0, and all other distances are infinity. Okay, so that means here we haven't started applying our algorithm over a graph. So this will be your first step. Okay, so now how can you compute the data of the second step? So for this one, you can either use the graph, or we have a very simple formula over Bellman-Ford algorithm. It says that that the distance of a vertex j. So this is the new distance, whatever we are computing in the first step. Okay, so here, or else just for not confusing, we can say that, okay, our first step is just 1, and so this is your first step. So here all the distances are 0, infinity, infinity, and so on. So for computing the distances on the second step, we will use this formula. So it says that the distance of vertex j, that is the distance of the vertex j in second step, this is actually equal to the minimum of two quantities. So what are these two quantities? So first one is the distance of vertex j in the first step. So you can either take this quantity, or you will take distance of the distance of all its neighbor, distance of all the neighbors of j, plus the, suppose k is the neighbor of j, plus the weight of the edge k comma j. Okay, so what you will do first, after writing down the first step, for computing the entries in the second step, we'll use this formula, that distance of the vertex j, this is actually equal to the minimum of either the distance of the vertex j in the previous step, which whatever distance we have in the previous step, or the distance of the vertex k plus the weight of the edge k comma j, where k is a neighbor of the particular vertex j. Okay, so we'll compute whatever, we'll take whatever minimum value among these values are there, right? So that will be your new distance of g. Okay, so this is one abstract formula, or else you can use the graph by saying the same thing. So initially what happened here, we won't use any edge or any neighbor, right? So in the second step, what happened, we try to locate the neighbors of 0. So that means in our given example, there are two neighbors of 0. right? 1 and 7. So this has distance 10, this has distance, I don't remember, maybe 8, right? So what we have done in the second steps, we have written down that the distance of the vertex 1 and the vertex 7 will change from infinity to 10 and infinity to 8, right? Because of this formula, or else we can say that we can use one edge to go from the vertex 0 to vertex 1, and we can go from vertex 0 to vertex 7. Okay, so that means what is happening here. So here in this step, we initially not moving at all, right? So now here what we are saying, here we will compute the distance of all those vertices, which can be reached from source vertex directly, right? So what is happening in the initial step, we are not moving at all. So we are saying that, okay, we cannot go anywhere except our source vertex. So they say that the distance of source vertex to itself is 0 and all other distances are infinity. In the second step, what we are doing, we are trying to go at those vertices which are directly connected to our source vertex by some edges, and we are updating the distance whatever weights are there for those edges. Okay, so that means at the first at this particular step, at the second step, we are going to those places which are which can be directly reached by the source vertex. And now here in the next step, what we are doing, so here whatever vertices we are getting, so in the next step, we are reaching all those vertices which can be reached by all those vertices which can be directly reached by 0. So right, so that means here those vertices, we are updating the distance of those vertices which can be directly reached by our source vertex. And now we are using the same repeating the same thing, but now we are taking care of all those vertices too which can be directly reached by source vertex, right? So that means here we are allowing, so we can use at max 2 edges, right? So in this step we can use at max 1 edge, right? In the next step we can use at max 2 edges. So here you can use here I am writing at max because it is possible to reach from a vertex, reach from a source vertex directly, so we don't actually need 2 edges. So that's why here distance of the neighbors of 0 will stay as it. That's why we are writing at max. Okay, so you can use at max 2 edges, and you will repeat the same thing over and over.
What did
Sorry,
you
what?
say? How do you arrive the third column? This first one is infinity. After that, the second column I understand. How did you calculate that next one?
Yeah, so what is happening? We reached from 0 to 2 vertices, 7 and 1, right? So now
Okay.
what we are doing, we are trying to figure out all those vertices which can be reached by the 7 or by the 1 or by the 0 itself. But these things is already taken care of. So that's why we are saying that, okay, in this step, you can use at max 2 edges. So whatever, so I think in the example 6 is there. So you can use 2 edges to reach from the vertex 0 to 6. Okay, so you are taking care of these edges, these vertices in the next step.
Okay.
And also we'll go further and further. So whatever the distance will get updated, we'll use the same thing. Now see what happened as far as I remember, in the next step what happened, there is a negative edge from the vertex 6 to 1, right? So here what is the thing is happening, that the distance of 0 to 1 is 10, but if you use this particular path, you will get some negative. So suppose there is minus 4, and here I guess that was 8 and 1, right? So that means if you use the circle path, that is 0 to 7, then 7 to 6, and then 6 to 1, then the cost of this path or the weight of this particular path is nothing but 8 plus 1 minus 4, so which is 5, right? So what we have done, in the next step we will update the distance of the vertex 1 to 5, and here we can use at max 3 edges, right? So here we can use at max 3 edges in the next step, first edge, second edge, and third edge. So that's why we are stopping at n minus 1 iteration. But here, since we started with 0, so it counted to n. So what has happened at the last step, you can use at max n minus 1 edges. But we know that if we have a graph, then that particular graph, the maximum length of a path could be n minus 1, right? So because of that particular fact, we will stop at the last step, n minus 1 step. Okay, is that clear now? So I think yeah.
Ma'am, nth iteration means n minus 1 edges, right?
Yeah, nth iteration means n minus 1 edges. That you can use at max n minus 1 edges. But this iteration will cover all possible paths, because we know that in a graph, we can have the length of a path can be at max n minus 1 edges, right? Because obviously if there are n vertices, then for creating a path you need n minus 1 edges. So in that path you will use all the vertices. That's why we have to stop at this particular step. But if you go with the formula, you will arrive you can go further up to whatever step you need. But the fact is we need to stop over here. The n minus 1th, the nth iteration means we have to use n minus 1 edges.
Yeah, like in 11.6 activity, we have a question in which they have asked a seventh iteration. That means we
Yeah.
have to check till 6 edges.
Yeah, I guess so. 7th iteration. So they will consider this as a first iteration. So I think they won't consider it this to be as a first iteration. For them, first iteration is this one. So this is your first iteration. So that means 7th iteration means the 8th step. So I think I have confused you guys. So actually what happens, so for iteration means whatever we are counting, we are getting something new. So this is your initial step. Okay, so this is your initial step. This will be your first iteration. Now this will be your second iteration. And so on. At the end, you will have your n minus 1 iteration, and here you will stop.
So number of iterations equals number of edges.
Yeah, number of iterations equals number of edges.
Okay, ma'am.
Okay.
Can you please fill a table with a small graph?
Yeah, we can. So we can discuss that particular question itself. Na? So what is that question? Week 11?
11.6.
Yes, I think it's
11 point?
practice assignment 6, right?
11.6 first question.
Yeah. So this is the question. Is my screen visible to everyone?
Yes, ma'am.
Yes, ma'am.
Yeah, so this is the question. So here what they ask, so while using Bellman-Ford algorithm for the graph shown in the below figure, dv the shortest distance of the vertex v from the source vertex after 7th iteration. Suppose the source vertex is 0, then which of the following options is true? So yeah, so 7th iteration means here 7th iteration means we have to do 8 steps. So if we are using, first is our initial step, so that won't count as an iteration. Whatever the second step is, that is count as an iteration. So I'll just take this as our example and we can solve it. Okay, so suppose here I'll make a chart. So this is your 0th iteration. Okay, so that means you can consider this to be as your 0th iteration or the initial step. So initially the all distances are 0. So what is our source vertex here? Suppose the source vertex is 0 only. So distance of 0 to 0 is 0. All other distances are infinity. Right. So in the first iteration, what will happen? We will take those vertices in counts which can be directly reached by the vertex 0. Okay, so here in this graph, there are 3 outgoing edges from vertex 0. So that means the vertex 1, the vertex 4 and the vertex 7 can be reached by the vertex 0 directly. Okay, so this is your first iteration. So here I am writing down the number of iterations. Okay, so this is your 0th iteration, this is your first iteration. So in the first iteration, so the distance of 0 to 0 is 0. So only distance, whatever the distance will change are from of the vertex 1, or the vertex 4 and the vertex 7. So the distance of vertex 1 will be 10. The distance of vertex 7 will be 6. And the distance of vertex 4 will be 4. Right. So just 10, 4 and 6. And all other distance will remain infinity as it is. Okay, so here you can observe that in the next step we have used at max 1 edges. So that means those vertices which can be reached from the source vertex directly. Okay, so now in the second iteration, what we will do, we will take care of the neighbors of these vertices too. So that means which can be reached by the vertex 1, which can be reached by the vertex 4 and which can be reached by the vertex 7. Okay, so let's start with vertex 7. So from vertex 7 we can go to the vertex 6. And the weight of this particular edge is -2. Okay, so what will happen now? The distance of the vertex 6 will get updated from infinity to 6 minus 2, which is equal to 4. Right, and there is no other outgoing edges from vertex 7. Only one outgoing edge is there, which goes to the vertex 6, and we have updated the distance. Now we'll go to another vertex, which is vertex 4. Now here at vertex 4, you guys can see that there is no outgoing edges. So that means it won't help us at all. So what we'll do, we'll go to another vertex, which is our vertex number 1. So from vertex 1, there is only one outgoing edge to vertex 2, and the cost of that is 1. What we'll do, we'll update the distance of the vertex 2 with from infinity to 1. Okay, so here in the next step, what happens? 0 is there, 10 will remain as it is. This infinity will change to 1. This infinity will remain as it is. This 4 remain as it is. This infinity remain as it is.
Ma'am, it should be
Sorry,
11.
11 what?
10 plus 1, 11 in second iteration for the case of second vertex.
Oh, sorry, yeah. Yeah, so 10 plus 1 will be 11. So this is 10, and we have to consider this distance from source vertex, right? So here I had added, but here I not. So thank you. So 10 plus 1 will be 11. So this distance will be changed from infinity to 11. And the distance of vertex 7 will remain as it is. Okay. So now in the third iteration, what we will do, we will take care of their neighbors too. Okay. So here you may think that, okay, it's now it is possible to make a mistake. So what you can do, you can use your formula that we know that the distance of a vertex j is nothing but the minimum of distance of j, which whatever we have found in the previous step, or else the distance of a vertex k plus the weight of an edge which is reaching to the vertex j. Right, so you can use this formula if you are thinking that, okay, we might miss some information in some bigger graphs. Okay, so now let's go to the third iteration. So in third iteration, what we will do, we will use at max 3 edges, right? So or we will take care of the neighbors of whatever new vertices, whatever new distances we have found. Okay, so we know that the distance of vertex 2 is 11 now. So what we can do, we can take care of the outgoing edges of this particular vertex 2. So there are two outgoing edges. One is going to 7 and another one is going to 5. Right. So now we can also think about that. Is it possible to get a minimum distance of vertex 7 rather than 6? Okay. So here what you can do, you can apply the formula for distance of vertex 7. So the distance of vertex 7 will be minimum of the distance of vertex 7 computed in the previous step. What is the distance of vertex 7 computed in the previous step is 6, right? Comma, you will take care of the neighbors of 7. You will take care of those vertices which are the neighbors of 7. So what are those vertices which are throwing edges at vertex 7? So that means you have to take care of incoming edges. So we have to find out distance of 0 plus the weight, which is 6, or the distance of 2 plus the weight, which is minus 8 here, plus of minus 8. Minus 8. Okay, so now here you can observe that, so this is nothing but equal to minimum of this is 6, distance of 0 is 0 plus 6 will be 6, and here distance of 2 is 11, so 11 minus 8 will give us 3. So here the minimum is 3, so that means the distance of vertex 7 will change from 6 to 3. Okay, is that clear now?
Well, in this case, only 2 inputs are going to 7, right? So if we are assuming that we have 3 inputs going to 7, so we have to take the least out of that, or how?
Yeah, you have to
the
take the least of that. You have to take the least of that. But what happened here, I have used this formula in case of 2, because now the distance of 2 becomes finite. In the previous cases, in the previous steps, what is happening? The distance of 2 is infinity. So that's why if you take minimum, you ultimately, the only possible distance is there is 6, right? So that means in the first step also you can apply the same formula. So in the first step also, distance of 7. Suppose I am applying this formula in the first, for computing the first step. It says that distance of 7 in the previous step, which is infinity, comma, distance of 0 plus the weight, which is 6, comma, distance of 2 plus the weight, which is minus 8. Okay. But what is happening here? This distance is 0, but this distance is infinity, because here we have to take care of the distances which have computed in the previous step. Okay. So here also, if you apply the formula, you will get distance of 7 is nothing but infinity, 6 and infinity. So we have to take the minimum of them, right? So the minimum will be 6 only. So that's why here distance of 7 is nothing but 6. Okay. So if you miss some edges, or if you think that this outgoing and incoming edges are a little difficult to compute, you can just blindly apply the formula. Write down all the neighbors which are throwing edges on that particular vertex plus the weights. Okay. Is that clear now?
Yes, this makes it clear.
Yeah. Any doubt so far? Okay. So what has happened? We know that the new vertex, whatever distance is 6 and 2, right? So initially their distances were infinity,
no problem.
but now their
Happy
distances
New
are
Year.
7. Can Naren please mute yourself?
Sorry, ma'am.
Yeah. Okay. So now here the distance of source vertex will remain 0, 1 will remain 10 only, because see, there is no incoming edges. So the only effect of contribution over distance of 1 is by the source vertex. So that's why this will remain 10 throughout the process. Okay. So now for the vertex 2, there are only 1 and 2 incoming edges, but the distance of vertex 3 is infinity in the previous step. So that's why it will also remain 11. And the distance of vertex 3, so we can go from vertex 6. Okay, so here now we have a path to reach at vertex 3. Okay, and there is only one single edge, so that means the distance of a vertex 3 will be equal to this. We can go to 0 to 7, 7 to 6, and then 6 to 3, right? So it's 6 minus 2 plus 4, so it will be equal to 8. So that means distance of vertex 3 will be 8. So now here what you can do, you can see that those vertices which has only one single neighbor, so that means those vertices which has only one single incoming edges, their distance won't get updated at all. For example, here the vertex 1 has only one single incoming edge, so the distance of vertex 1 will remain 10 only, because there is only one path to reach at vertex 1. Okay, so the choices occurs if and only if there are multiple paths to reach at that particular vertex. Okay, but if there are some vertices which has only one incoming edge throwing at them, that means there is only one path by which we can reach at that particular vertex. So their distances won't get updated at all. For example, this one is there. What is another one? Here we have two paths. So it is possible to reach at vertex 2 by two different paths. Okay, here also we have two different paths, two incoming edges at vertex 7. So it is possible to reach at 7 by two different paths. Okay, here also it is possible. Here it cannot be possible. So that means the distance of 5 will remain as it is throughout the process. Whatever distance we will compute now, that will remain as it. Similarly, for vertex 4 also the distance will remain as it is. For vertex 3 also the distance will remain as it is. So that means for these vertices, the distance won't change at all, because there is only one possible path to reach at those vertices, since there is only one incoming edge. Okay, is that clear to everyone? Yeah.
But for 4, there are 3 incoming edges, right?
Yeah, sorry. Yeah. I thought those are outgoing edges. Thank you. So yeah, I was talking about incoming edges only. So those vertices which has only one incoming edge, so it is only possible to reach at that vertex by a single path. So that path will be of minimum cost, right? Okay, so the distance of vertex 3 will remain as it is. The distance of vertex 4. Okay, so what are the neighbors of vertex 4? So neighbors of vertex 4 are 5, 3 and 0. So by 0, we have already computed the distance. That distance is 4. Distance of vertex 5 is infinity in the previous step, so it won't affect. Distance of 3 is also infinity in the previous step, so it won't affect. So that means here the distance will remain as it is 4. Now let's go to 5. So now is it possible to reach at vertex 5?
The distance of 3 is 8, no? From that we can compute the
No,
distance.
we have to take care of account of previous step, not
Previous.
the
Okay.
previous step.
Okay.
This 8 will contribute into next step. Okay, so now let's go to the vertex 5. So we can reach at vertex 5 by vertex 2, right? So we can start from vertex 0, go to vertex number 1. From 1 we can go to 2, and from 2 we can go to 5. Okay, so that is the distance of the vertex 5 is 10 plus 1, and this weight is minus 10, right? So 10 plus 1 minus 10. So which is equal to 1. So that means the distance of the vertex 5 is 1. Now what will be the distance of vertex 6 now? So see, at vertex 6 there are two incoming edges. One is from 7. So we have already taken care of that 7 in the previous steps. And another one is 5. But in the previous step, the distance of 5 is infinity. So the minimum distance will remain 4 as it is. Okay, so this will be your what you can say, third iteration. Now let's go to the fourth iteration. So in the fourth iteration, the 0 will, so see.
How did you compute that 5? Vertex 5? The distance is 1, no?
Yeah, so for the vertex 5, we can start from 0, go to 1, go to 2.
Sorry, I got the 6.
Okay.
6
for
is
vertex,
no?
Yeah, so for vertex 6 is distance is 4. See what happened, the distance of 6 is distance of 6 in the previous step, which is 4. Right, so we are taking this particular 4, comma. There are two neighbors, right? Distance of 7 plus the weight, which is minus 2, or distance of 5 plus the weight, which is 1. Right?
Okay.
But these distances are distances taken care in the previous step. So in the previous step, the distance of vertex 7 is 6. So this is equal to 6 minus 2, which is 4. And here the vertex 5 has distance infinity, right? In the previous step. So that's why infinity plus 1 will be infinity. So minimum will be 4, right?
Okay, understood.
So now let's go to the next step, fourth iteration. So we know that this 1 and this 5 and what was the another neighbor which has only one incoming edge, this 3. So these distances won't change at all. So this will be 10 and the distance of 3 will remain 8 as it is, and the distance of 5 will remain 1 as it is. Okay, now let's go to another vertices. So vertex number 2. So let's go to vertex number 2. So there are two incoming edges. One is coming from 1. Another one is coming from 3. Okay. So the distance of 2 will be the minimum of whatever distance we have in the previous step, which is nothing but 11. Or else we can start from 0, then go to 1, then go to 2. So which is 10 plus 11 is 11. Or else we can follow this rounded path. So that is, we can start with 0, go to 7. So 0 to 7, then 7 to 6. Then 6 to 3, and then 3 to 2. Let's see what will be the cost of this particular path. So that cost will be 6 minus 2 plus 4 and 20, right? Plus 20. This 6 minus 2 plus 4 and this is 20. Okay, so this cost will be obviously more than 11, right? So it will be 28. So the minimum is 11, so it will stay 11 as it is. Now here also you have to observe that we have taken care of both edges. So that means if you reach the vertex 2 from this particular edge, the cost will be 11 of that particular path. And if you reach the vertex 2 from this edge, the cost will be 28. So that means the minimum cost to reach at vertex 2 is nothing but 11. So this 11 will remain as it is throughout. So what are the distances that are fixed now? So distance of 1 is fixed to be 10. Distance of the vertex 4 is fixed to be 4. No, sorry, distance of not 4, no, it's 5. Right? Those vertices which has only one incoming edge. So 1 is there, 5 is there, and 3 is there. So that means distance of 5 is now fixed to equal to 1. Distance of 3 is fixed to 8 because there is only one path. Now what happened? At vertex 2 also it is possible to reach at vertex 2 using two paths, right? But still there could be some choices. So let's see. Because of the distance, if the distances of their neighbors will change, then their distances might change. Okay. So let's see what we can do. Let's go to vertex 4. So for vertex 4, we can reach from vertex 5, we can reach from vertex 3, and we can also reach from vertex 0. So let's see what will happen for vertex 4. So the distance of vertex 4, if you reach from directly from the vertex 0, it will is nothing but 4. If you try to reach from vertex 3, then what you have to do? You have to first come to 3, right? And what is the distance of 3 in the previous step? It's 8. So that is 8 plus the weight, which is minus 3. So 8 plus minus 3 will be 5, right? Now another thing is you can reach at vertex 5, vertex 4 using the vertex 5. So what is the distance of vertex 5? Which is 1. So 1 plus 5, which is equal to 6. So that means the distance of vertex 4 will remain 4 as it is. Now let's go to the vertex number 6. So we have to do the same thing for each and every vertex now. So the distance of vertex 6, this is equal to the original distance is 4, comma, we can reach vertex 6 by vertex 7. So is there any update in vertex 7? Yes, so there is an update at distance at 7. So that is the distance of 7, which is 3, plus the weight, right? So we can reach at 6 by vertex 7. So the distance of 7 is 3. Now in the previous step, the distance of 7 is 3. So 3 minus 2, right? And we can reach at vertex 6 by vertex 5 also. So this is 1 plus 1 because the distance of 5 is 1, right? This is. So now here the distance of vertex 6 is 4, minimum of, obviously, minimum of 4, and here 3 minus 2 will become 1, 1 plus 1 will become 2. That means now distance will get updated to 1.
And 1 no, madam.
Yeah, 1. Okay. Now let's go to vertex 7 again. So see, that's why applying formula is much easier than going via the graph, because by the graph it is possible to get lost or get a little bit confused. Okay, so distance of 7 will be again whatever distance we have in the initial step, which is 3. Now for 7, it is possible to reach from 0, reach from 2. If you go from 0, you will get 6. And if you go from 2, what is the distance of vertex 2 in the previous step? That's 11.
11 minus
So 11 minus 8, which is 3. So ultimately this distance will remain 3 as it is. Okay, so this is your fourth iteration. Is there any update? So yes, there is one update. We have changed the distance of 6 from 4 to 1. So that means all those neighbors which are connected by 6, now it is possible to get a minimum distance for those neighbors too, right? So that's why we have to repeat it again and again and again. So this is your fifth iteration. Okay, so the distance of 0 to 0 is 0. So for vertex 1, there is only incoming edge from source vertex. So this will remain 10 as it is. For vertex 2, we can come from vertex 1. So but the distance of vertex 1 is 10. So 10 plus 1 will be 11. So if you reach by this particular path, this is 11. Another path to reach at vertex 2 is going from vertex 6. And we have an updation for distance of vertex 6, right? So it is possible to get a minimum distance now. So let's see what is the distance of vertex 2. So it is the
But
initial distance.
mechanically, we can do, madam. Instead of saying that, seeing the graph, we can just say 2 can be reached via 1 and 3. So 1 is there, and what is the 1? 10 plus 1 is 11. And
11.
here 2 is 11. 11 plus 20 will be 21. So as of now, it will be same like that. We can, without
Yeah,
seeing
we
the graph
can.
also, we can do, no?
Yeah, that's also we can do. We can directly use that path. Okay, we have to go here, or here, here, and then go here. Right?
Okay, continue, madam, please. Sorry.
Yeah. So still the things will remain same, but here there is one. What I was telling. We have get an update over the distance of 6, right? Distance of 6 is 1 now. Okay, let's see.
Where I told how to identify now. See, should we go to 6 first from
That
2?
distance which I have given 1. Yeah,
Because as per the
Mm.
algorithm, directly next second round, if I'm going
Mm.
for our vertex 2, already 11 is there, and it can be
Mm.
reached by via 1 and via 3. So 3 is 8 is there already.
Yeah.
I mean, then it will be 3 plus 20, no? Something like that? Or why we, or
Mm.
how we have to identify, we have to come by 6 by seeing the table?
Yeah, sorry.
Or should we start from 6? How is that?
No,
Should we
no.
start from 0, 1, 2, 3 same way, or wherever changes are there, that from like that you have to change? How to compute the 5th iteration?
No. This will remain 11 as it is because there is no updation in distance of 3 in the previous step, right? So I jump it to 6, but you have to locate the neighbors only. So there is
Neighbors
no
only.
updation in distance of 1 and distance of 3, right? So they have remain as it is. 3 remain 8 as it is, and 1 is remain as it is. So that's why this won't change. It will stick to 11 only.
Okay. So is it better to see wherever the updation is there, you can go to that vertex and check for the changes?
Yeah, correct.
Like,
So
because
you have to see wherever the updations is there.
so 3 from 6 you can go to 3 and only 3 we can go. So only
Yeah,
for
only
3 if
3.
you check it is enough, no?
Yes, it is enough for checking only 3. So the distance of 3 will become, so original distance is 8. Now here there is only one possible way we can reach from vertex 6. So that was nothing but 1 plus the weight.
8.
1 plus weight is 4.
4.
Right? The distance will change from 8 to 5 now.
All others will be same only, no,
All
madam?
others will be same as
So
it
again,
is.
in the next iteration, only for 3, if we
You
check
have
that
to
is
check.
enough.
Yeah, correct. In the next iteration, if you check only for 3, because the distance is changed only for 3, so all other things will remain as it is in the 6th
How
iteration.
the distance of 3 changed?
Because the distance of 6 changed, right?
Oh.
And there is a direct way to go to 3.
Okay. Okay.
Okay.
But you identify the updations with different colors. In exam, we do have many color paper pens.
Yeah, that's correct. So what you in exam, this type of question won't be there because it is taking
Oh.
at least half an hour, right?
Oh.
Yeah, this is only for your practice because in exam you have to solve so many questions. So either we can ask up to first iteration, second iteration, or
Oh.
else we will give such a table and there will be some filling the blanks.
Okay.
So this type of question would be there, but you don't need to build the whole table.
Oh.
Okay, because it will take time. That's all. That's
Oh.
the only reason. Okay, so in the 6th one, what we'll do, we'll go to only those vertices which has updation, right? So we have changed from 8 to 5, right? 0, 0, 10, 10, 11, 8 to 5, 4, 4, and all things are there. So from 3, we can reach to vertex 2. From 3, we can reach to vertex 4, right? So what will be the distance of 2 now? So distance of 2 will be the initial distance. The initial distance is 11, comma. Now distance of 3 plus the edge, which is 20 plus distance of 3, which is 5. Again, it is 25. And distance of 1 plus what that is 11 only. So that means here also there won't be any update. This 11 will remain as it is, right? Because the minimum is 11. Okay. So distance of 3 will remain as it is, only distance of 4 will change. So now let's go to the distance of vertex 4. So initially the distance of vertex 4 is, in the previous step, the distance of vertex 4 is 4. So this is 4 comma, and now at 4 we can reach from 0, we can reach from 5, we can reach from 3, right? So if you reach from 4, so that means the only updation is there in 3. So yeah, so let's start with 0. So if you reach from 0, there will be, answer will be 4. If you reach from 5, so the distance of 5 in the previous step is 1. So this is 1 plus 5, which is equal to 6. And if you come from the vertex 3, so from the vertex 3, this is 5 minus 3, which is 2. So that means here the minimum will change. And now the distance of vertex 4 is 2. Is that okay? Now here we have an updation. We changed from 4 to 2. Okay, all other thing will remain as it is. 1, 1, 3. I hope we have computed the correct distances. Okay, so this is your last iteration. So here 0 will be there. So only update is there in 4. And from 4 there is no outgoing edges. So that means it won't affect the distance of any other vertex. So that means all values will remain as it is. Okay, so let's see. We have for 5, 6, we have 1 is there, right? Distance of these are the distances. So this is the distance of 0, this is the 1, this is 2, 3, 4, 5, 6, and 7. Okay, so for 5 and 6 the value is 1, which is correct. For 3 the value is 5, which is also correct. For 4 the value is 2. This option is also true. And for 4 the value is 5, so this option is wrong. Okay, so the correct answers are 1, 2, and 3. Are we okay with this?
Yes, ma'am.
Yes, ma'am, this is pretty good. Yeah.
Okay, yeah. So now I think it is much clearer how to find the updates, right?
Surely.
Yeah. So I think this abstract formula works better than working on the graph with all the edges and things.
Yeah, if the graph is bigger, then actually it is difficult. But one point that Naren says that you have to check for only those vertices which has updation in the previous step. So this point you can remember.
Yes, because DJs and DKs which we are taking, they're already being taken in the previous steps only. So
Yeah, right.
the iterations are taken in the previous values only.
Right. So it's better to go with the formula if you have, so here we have 8 vertices. So in 8 vertices it is possible to get lost or at some place, right? Okay.
Ma'am,
Now
can we discuss the second one as well? Second question.
yeah. So what is the second question? If the source vertex is changed from 0 to vertex 4, then which of the following options are correct? Bellman-Ford algorithm stabilizes after the first iteration. Will not be applicable. dv is finite for some vertex v other than source vertex. None of the above. Okay. So here what is happening? If you change your source vertex from vertex 0 to vertex 4, so what is happening? There is no outgoing edges from vertex 4. So that means you cannot reach to any vertex from this particular vertex 4. So if you find out the table here, the only source vertex will have 0 entries and all other entries will be infinity, right? Because we cannot reach at any
Screen
other
is not
vertex from
visible, I
vertex 4.
think.
Oh, sorry. Yeah, actually today I'm using from browser, so it's.
So, ma'am, it won't be 0th iteration. It will be first iteration, right?
No. It will be 0. So what is 0th iteration is our first step. Okay, my screen is visible now.
No, but in the options it is written stabilizes after the first iteration. So first iteration means first edge, one
Yeah,
edge. And we
yeah,
cannot move from 4.
yeah. We cannot move from 4.
So that means 0th iteration is first iteration in this question, right?
Yeah, because we are not at all moving. So that means Bellman-Ford algorithm stabilize after the first iteration. After the first iteration, it will already stabilized. So I don't know what this means. So is this option is correct? So I think this will be correct. So it is already stabilized because the data will be only 0 and all other things are infinity. But why you need to do the first iteration? Yeah, correct. Okay, so now I got it. So what happened? So this is our 0th iteration. So the 0th iteration, 0, 1, 2, 3, 4, 5, 6, suppose there are, so this will be 0 and all other things are infinity, right? So if you compute your first iteration, the quantities will be same as it is. And after this iteration also, the all things will remain as it is. So I think that's the meaning of stabilize. So after what iteration, you are getting the same type of data. So that means same entries are repeating again and again and again. So I think at that step, they are saying that this particular algorithm actually stabilize. So we can say that this algorithm will stabilize at the first iteration, after the first iteration.
Ma'am, so that in that case, it should be 0th iteration or it should be first step, right?
Uh, I think this one, they say the first iteration, this is correct because see, if we are at 0th iteration, we haven't done anything at all. We have just writing. We have just pointed out. We are just standing at our source vertex. We haven't gone anywhere, right? But after the first iteration, we will figure it out. Okay, there is no way to go anywhere from this particular vertex. So we can say that it stabilizes after the first iteration.
Okay.
Okay, but such type of confusing wordings won't be there in the exams because here the iterations, the in the lecture, sir haven't defined what is the first iteration, what is the second iteration, right?
Yes,
If I'm
ma'am.
not wrong. Yeah, so such type of confusing wordings won't be there. In the exam, we will clearly mention which step you have to check or which step you have to, or which iteration you have to mention. Okay.
Okay, ma'am.
So let's look at the last question also of this activity. So here in the last question, for what value of x can we use the Bellman-Ford algorithm to find the shortest path from the vertex 0 to every other vertex in this graph below? Okay, so here what is happening, what you need to check when we cannot apply Bellman-Ford algorithm?
If there are no negative cycles, we are not
Yeah,
allowed.
correct. So that means you need to find out all those values of x for which you are getting negative cycles. Okay, so here this x is contributing into one cycle.
We're not seeing your screen. We are just seeing just your previous screen.
Yeah.
Only
So
with the-
I'll draw the graph actually. So this something like this is there. Right. Okay. So this is your graph. This is the value of x. Here it is 4. Here it is 3. Right. So here you can observe that this particular edge will create a cycle. If you take a certain value, whatever value of x you will take, ultimately you are getting a cycle over here using the value of x only. Right. There is no any other cycle formed in this particular graph. This is your vertex 0. Right. So we have one cycle. We can start with 1. We can go to 2. Sorry, we can go to 4 and 4 to 2 and then 2 to 1. So here the values are 4, 3 and x. So what are those values of x for which this cycle will become negative cycles, right? So this thing you need to figure it out. So it's kind of obvious since what we want all those values of x for which this particular sum will be less than 0, right? So that is x plus 7 will be less than 0. So that means x should be less than minus 7. So that means if you take any value of x which is strictly less than minus 7, this will become a negative cycle.
But we also have a path from 1 to 4 and 3, but the weights are not given there.
No, the weights are also given there. 1, 5 is there. I have just.
Okay. But then we can choose that also is another cycle, right?
No, but this direction won't allow us.
Okay. Right. There's only one there, correct. Right.
Yeah. Similarly, you can also take care of this bigger one, but again, the directions are in such a way that this won't make a cycle.
Okay, only one cycle is possible, which is
Yeah.
1, 4, 2, 1.
Yeah, correct. Fine. So this is 11.6. Now let's go to practice assignment. So is there any doubt from practice assignment? I'll share my screen and then we can discuss it one by one. Yeah, which question?
This one, x less than -7.
X less than minus. Yeah. So we have discussed, right? I mean, the value of x, whatever value we will take, which are less than minus. So that means x belongs to minus infinity to -7. Right?
Ma'am,
This interval
options are
will.
different.
Options are different. -6 to infinity, -7 to infinity. This for what value of x can use. Oh, okay. So that means if x belongs to, so that means if this x belongs to minus infinity to -7, then we will get a negative cycle. Right. So in this case, we will get a negative cycle. So that means if x does not belongs to minus infinity to -7, we won't get a negative cycle. So that means here we can apply the Bellman-Ford algorithm. So your x does not belongs to minus infinity to -7 means x belongs to -7 to infinity. So here if you choose any value of x, the cycle won't be a negative cycle, right? So that's why the correct option is -7 to infinity. So in this case, you can apply Bellman-Ford algorithm. So question was asked, find those values of x for which you can apply Bellman-Ford algorithm. So if you take any value of x which is strictly greater than -7, you won't get a negative cycle. So you can apply the Bellman-Ford algorithm. Is that okay?
Yes, ma'am.
Okay, fine.
The
Ma'am, I
seven.
have one more doubt.
Yeah.
Generally, the questions we have discussed, we do not take decimal value in case of weight. So
Yeah,
can the
correct.
answer be -6 to infinity?
No. It can be actually, right? So, but see, if you take any value from this interval, then no, so that's a good question actually. So if you take the value of x to be, so that means from your point of view, is this is a correct option, right? -6 to infinity. But if you take, yeah, but for that, -6 to infinity. Yeah, we can actually take the weights in the pointers. So that means it is possible to take the value of x to be -6.5. Then you will get a negative cycle. So yes, you can take the weights as the pointers too,
Okay, ma'am.
because there is no harm. So that's why they have given the intervals, I guess. In general, we won't take because then calculations will be difficult. But you can take weights as a pointer or any real number as your weight. Because see, real numbers means it is possible to get such type of quantities. Okay.
Got it.
I mean, in your calculation, you said greater than, if you can slightly go up. Yeah, x is less than -7, right?
Yeah. If you
So,
take x is less than -7, then you will get a negative cycle.
so that means anything from starting from -7,
Yeah,
uh,
-7 to infinity.
infinity. But you're saying
Yeah, but
-7 excluded.
see,
You're excluding -7. So I
because
don't.
this is given in the option.
Okay. But
So
but
for these
technically,
values,
-7 is included in the
yeah,
positive cycle, not the negative
yeah,
cycle, right?
not the negative cycle.
Okay, understood.
Okay, now let's go to practice assignment.
Can you discuss the PA 3 and 9?
Yeah, sure.
Question 3 and 9. Oh, I think, yeah, sorry. Questions might be different. I mean,
Mhm.
might have been shuffled. So
So this is P, na?
yes, yes,
Yes, ma'am.
yes, ma'am. Yeah,
Question number 3, na?
3. Three
Yeah.
and
So here it involves actually so many calculation, but let's see what we can try, right? But we will go by the intuition. We won't go by that first compute SP1, then SP2, SP3. We won't go like that. We'll just say that what is the meaning of SP4 and then compute the matrix. Okay. would be better if I used. Okay, so here we need to compute SP4. Okay, so again SP4 will be a matrix of size n by n. N is the number of vertices. So here there are 6 vertices. So that means it will be a matrix of size 6 by 6. Now what is the entry of SP4 of I comma j? SP4 of I comma j is the length of shortest path. Length of shortest path via the vertices 0 to 3. Right, 0, 1, 2, 3. So that means you can use the vertex 0, 1, 2 and 3 from reaching any vertex to any other vertex. Okay, and you have to compute the length of that particular shortest path. Now we know that since there are no loop edges, so that means there is no edges from starting from, okay, but here we have 4 vertices. So it is possible to get some entries over the diagonals too. Okay, so this is your SP4. So here are vertices 0, 1, 2, 3, 4 and 5. And here there are 0, 1, 2, 3, 4 and 5. Okay. So now let's start with 0. So is it possible to get back at 0 using these vertices? So I think it is possible because we can start with 0. No, it is not possible because there is no way to get out of this particular vertex 0, right?
Because
So
there is no outgoing edge.
there is no outgoing edges. So that means this all things are infinity. We cannot go to vertex 0 by we cannot go from vertex 0 to any other vertex. Okay, so is the options are different from this thing? No, all options contains the first row is infinity. Fine. So 0 is all. Now let's go to vertex 1. So now where we can go from vertex 1? So we can go from vertex 1 to vertex 0. So let's see how many ways are there to reach at vertex 0 from vertex 1. So there is one direct way and the cost of this path is 1. Okay, so we have one path which goes from which moves like we can go 1 to 0 directly. Is there any other vertex which we can use? So we can go to, from 1 we can go to vertex 3, but from 3 if you want to get out you have to use the vertex number 5, right? But in our restriction, since we are talking about SP4, then we can use only 4 vertices and those 4 vertices are 0, 1, 2, 3. So we cannot use vertex 4 and vertex 5. So that means it is only possible to reach at vertex 0 from vertex 1 is just by using this particular direct edge. Okay, so that means this particular quantity will be equal to 1. Okay, is that clear? Any doubt in this one?
It's fine.
Right. Now let's try to reach from vertex 1 to vertex 1 using the vertices 2, 3. So as we known, we can go from vertex 1 to vertex 0, but we cannot get out of this particular vertex 0 because there are no outgoing edges. So that means this path is blocked to us. We cannot go anywhere. But similarly, we can go to vertex 3, but from vertex 3 we can only go to vertex 5, which is not included in our, which we don't want to include in our particular path. So that means from vertex 1, I cannot reach it to any other vertex other than 3. Okay, so that means we cannot come back to vertex 1 using those vertices. We cannot go to vertex 2 also. We can go to vertex 3 and the path is nothing but 2. The length of the shortest path is nothing but 2 because there is only one path. Okay, and we cannot go to vertex 4 either. We cannot go to vertex 5 also. We can go to vertex 5 actually. But yeah, so vertex 5 could be the end point of the path, right? So we
Could
can
be
reach
minus
from
1.
vertex 1 to vertex 5, yeah, using 3
But
to
5 is not included, right, man? 5 is not
yeah,
included in
but
our.
5 is the end point of the path. So we have to use these vertices as the in what you can say in between the path. So we have to
Okay,
start
okay,
with 1, we have to go to 5. we have to use these vertices as the middle vertex of our paths.
Okay. So since 3 is a part of our in our
3 is a part of our set, so
system,
we can use,
so we have to consider 5 also in that case.
Yeah. Okay. So that means we can reach to vertex 5 using 1, and the distance will be minus of 3. Fine. Is there any? Okay, so there is only 2 options which include minus 3. So let's see.
We can also reach from 2 to 5, right?
2 to 5. But how we can go to 2 by 1? From 1. If you want to reach 1.
Oh, I see. Okay.
Okay.
Yeah.
Yeah, it's good. If we solve together, then we won't mess it up. Okay. Now let's start from vertex 2. So from vertex 2, what are the ways, what are the paths we can find? So from vertex 2, we can go to vertex 0 by the straight edge, which is minus 4.
Minus
So,
4.
Right. So 2 to 0 we can go, and the path is minus 4. But is there any path we can use? So from vertex 2, we can also go to vertex 1, and from vertex 1 also we can go to vertex 0. So that means there are 2 paths to reach at vertex 0 from vertex 2. One is the direct one, another one is this 1 to 0. But the cost of that path is 3, so which is not a minimum one, right? So minimum one is minus 4. That's why you need to choose minus 4 here. Okay. So here we have to consider the possibilities too. So that means how many paths are there and which one will be of the minimum cost. Okay. So now let's go to vertex 1 from vertex 2. So we have to reach from 2 to 1. What are the ways are there? So one way is the direct way. So we can go directly by just 2. Now another way is there is no other way, because there is only one way, since there is only one incoming edge. So that means this will be equal to 2 only. Now can we circle back to the vertex 2? Okay, so let us think. So here there is only one incoming edge which are coming back to 2. So we need to find out the path between vertex 2 to 2 using these vertices. Okay. So there is only one path which are incoming to 2, that is used. I mean, we need to use the vertex 4 as the in between vertex of that particular path, right? But 4 is not in our set, so we cannot do. Okay, so this will be infinity. Is that okay for everyone?
4 is not in our set, but you have to still consider, because 2, 3, 3. Okay, there is no link to between 3 and 4.
Yeah, but if there is a link, still you cannot use 4 as in between any path. Okay, you can use 4 as the end point.
It's not an end point. Okay.
It's not an end point. So you can use 4 and 5 as the end point of the path, but you cannot use them in between the path. Okay. Now let's try to go from vertex 2 to vertex 3. Okay. So for vertex 3, there are 3 incoming edges. One is coming directly from 2. So we can directly go by this path, which is of cost minus 1. Or else we can go to, we can start with 2. We can go to 1. And then from 1, we can go to 3. And the cost of this path will be 2 plus 2, which is equal to 4. Right? So this cost is 4. This cost is minus 1. Is there any way to reach at vertex 3 from vertex 2? So no, there are no other ways. So that means the minimum is
minus 1.
Yeah. So is there any path from 2 to 4? So over 4, there is only one incoming edge, and that is coming from 5. But we know that if you want to go from vertex 2 to 4, you have to go to vertex 5. But we cannot use 5 as our in between as the intermediate vertex. So that's why we cannot go from vertex 2 to vertex 4. So that's why this distance will be infinity. Is that fine?
Yes, ma'am.
Yes?
Yeah. So only we can use only 0, 1, 2, 3 as only our intermediate edges, but if none of the edges should be acting as an intermediary.
None of the vertices other than these 4 vertices can act as an intermediate vertex. Okay, that is the meaning of SP4. So whatever power you have to take one less. So that means 4 is there. So you have to start with 0. So 0, 1, 2, 3, 4. 0, 1, 2, 3. Okay, you have to stop at 3. So if k is there, you have to stop at k minus 1. Okay. And now let's start with 2, and we have to go to vertex 5. So if you want to reach at vertex 5, the only incoming edge is from vertex 3. So okay, that means we have to go to 3. Now, what is the shortest path between 2 and 3? So the shortest path between 2 and 3 is -1. So you can start with 2, go to 3 by -1, and then you have to add it here -5. So the answer will be -6. Is that clear? Any doubt in this one?
Yes, ma'am, it's fine.
Fine. Okay, now let's go to 3. We'll do the same things. So from 3, let's think about 0. Is this possible? Is there any way to go to 0? So actually what has happened, from 3 there is only one outgoing edge, and that is going to vertex 5, right? So that means if you want to reach it some vertex from vertex 3, you have to use the vertex 5 as your intermediate vertex of a path, right? But we cannot use. So that means all distance will be infinity except 5, because we can go to 5 directly. We are not, if you are using this particular path, then here 5 is not an what I say now, in between or intermediate vertex. Okay, so this is not an intermediate vertex now. It is an end point of the path. So this is possible, and here the weight will be -5. Okay, is this particular row is clear? The row of vertex 3 to everyone? Is there any doubt?
Three, only one outgoing is there.
Yeah, only one outgoing edge is there, which is going to 5, and we
5.
cannot use 5 as in between vertex, so that's all.
Okay.
Okay, so now let's go to 4. So from 4, there are two outgoing edges. One is going to 3, another one is going to 2. So is it possible to reach from vertex 4 to vertex 0? So the answer is yes. We can follow this path, which is going to 2, and then from 2 we can go to 0. So 4 to 2, and then 2 to 0. And what is the cost? Cost is 4. This cost is 4, and this cost is -4. That means this entry will be 0, right? The total cost will be 0. And there is no other path to reach at vertex 0 from any other vertex.
No,
Right?
you can go from 4 to 1, 0, right?
Yeah, but we cannot reach at 1 because there is no incoming edge at 1. Sorry. Yes, that's correct.
Yeah,
We
4,
can
4
start
to 1, 0. Only
2
thing is
to
we
1.
need to check whether it's the lowest weightage or not.
Yeah, it won't be the lowest, I guess, because
Yeah.
from 4 to 2 all are positives.
Yeah,
So
all are positives.
4 to 1. Yeah, but it's good to notice. And there is another part too. Okay.
Right.
Now let's go to vertex number 1. So can we reach from 4 to 1? So the 1 path is obvious, and we obviously have to use 2 as the in-between vertex because that's the only thing which is connecting to 1, right? We have to start from 4 to 2 and then 2 to 1. So this cost us 6. Okay, now 4 to 2, there is only direct edge, and there is no any other edge, so this cost will be 4. From 4 to 3 also, there is a direct edge, but there is another path and there is one more path. So okay, so this one is noticeable. So
4 to 3 and 4 to 1, 3.
yeah, so 4 to 3, if you go directly, the cost will be 7, right? If you use 2 as your in between vertex, then the cost is little less, 4 minus 1, so the cost is 3. And if you use 2 and 1 both as in intermediate vertices, so that is, you'll start from 4, go to 2, then go to 1, then go to 3.
Was 8.
Right, so this will be 4 to 2. The cost will be 8. So here,
No, just a question. Like 4 to 0 should be updated to 7, right?
why is that?
Because you can reach from 4 to 0. So you take 4 to 2, go to 1, and then come to 0.
Yeah, but we are finding the length of the shortest path, right? So there are two paths. One
okay.
is of cost 0, and
Yeah.
another one is 7.
Sure.
So okay, so this will be the minimum, which is 3. Okay, now is it possible to circle back at vertex 4? So there is only one incoming edge at vertex 4, and that is also coming from vertex 5. But as our reasoning says that we cannot use 5 as the incoming vertex, so that's why this distance will become infinite.
Screen is not red.
Sorry, my screen is not visible?
Yeah. Some screen disappeared.
Yeah, I actually accidentally tapped to stop streaming. So Zoom only work if you have an app. It won't work nicely if you have browser. Okay, so let's let's go from the vertex 4 to vertex 5. Okay, so if you want to reach at vertex 5, you have to go to vertex 3 because there is only one path. So you can reach at vertex 5 only from vertex 3. But can we reach to vertex 4? So the answer is yes. And the shortest distance between vertex 4 to vertex 3 we just have computed, and that is our 3. So that means we can start with 4, go to vertex 2, then go to vertex 3, and then go to vertex 5. And this cost is 4 minus 1 minus 5. Okay, so this is 4 minus 1 minus 5. So this is 3 minus 5, which is equal to minus 2. So this will be minus 2. Okay, so now we arrive at the vertex 5. So from vertex 5, let's see, can we go to vertex 0? Can we go to vertex 1 and all those things? But what is happening here? From vertex 5, there is only one outgoing edge, and which is going to vertex number 4, right? So what we'll do, we'll use all the shortest path that we'll use all the things which are nearer to 4. That means from 5, I can just go to 4. But again, the thing is we cannot use 4 as our intermediate vertex. So that means everything will be infinity except the 4, just 6.
But
And
5 is not in our sequence right now. Maybe we are considering.
Yeah,
5.
but you can take 4 and 5 as the starting and end vertex of start and end vertex of path.
Okay.
Right.
So
So
starting
here
also
5,
we can consider. Okay.
yeah, starting also you can consider. Okay. So these things you need to, these vertices you have to use as intermediate vertex of path. But 4 and 5 we can use as the end vertices too. Okay, so here it will be 6. Here it will be infinity. So which option is correct? Let us see.
From 5 to 4, 4 to we can go any vertex, right?
Yeah, but we cannot use 4 as a between, so intermediate vertex.
Why, ma'am?
Because see, we are computing SP4, right? So whenever we are talking about SP4, the in between vertices, so that means those vertices which can use in between the paths are 0, 1, 2, and 3. You cannot use any other vertex in between your paths. So that means if you want to reach from vertex 5 to any other vertex, you are allowed to use only 0, 1, 2, and 3. That's all. So you can assume that you want to go somewhere, but the only possible stations or railway stations are these stations. So you can start with a station, start with at your place, and you can use only these 4 stations to arrive at some location. Okay, but this 4th vertex is not there, right? So if you want to get out from vertex 5, you have to use the vertex 4 because of this incoming edge, right?
Okay. In SP5, we can take that one.
Yeah, we cannot take that one but we can take 4 and 5 as end vertex of our path.
In SP5,
In SP5 you can take the vertex 4, but you cannot take the vertex 5. So SP4 is there, so we run up to 3. So if SP5 is there, we'll go up to 4. Okay, fine. What is the next question from practice assignment? This is correct actually. 0, 6, 4, 3, infinity minus 2.
Question number 9 with the NCST.
Question number 9. Yeah, find the weight of this minimum cost spanning tree. So here you can use any algorithm. Prim's algorithm also, Kruskal's algorithm also, whatever is comfortable to you.
I was using because here I'm using Prim's algorithm. So I started.
Okay.
So I started with A, okay, as my
Huh.
source vertex,
Okay.
and now I came to C.
Oh, see, Prim's algorithm. In Prim's algorithm, you have to choose the minimum edge. So if you are starting with A, you have to choose this particular
B, sorry.
edge.
Yeah, I
as
chose
your.
B. Yeah, I chose B, and then
Okay.
I came to C.
Then you came to C. Why you came by this edge, na? By 2 edge.
Yeah, because
Huh.
3 is less than 5, right?
Yeah.
Because I have to choose A to B, and I cannot choose C and go back to A. That's not possible because that will form a cycle. So I went from A to B and B to C, then C to D.
No. You went from B to C by this edge.
Yeah.
No, see, as you choose the A to B, you have three choices here for growing your tree, right? Prim's algorithm says that select a root as your minimum cost edge and then grow your tree. So for growing your tree, you can choose this edge as your branch, this edge your branch, and this edge as your branch, right? So three choices are there. So you have to choose the least one. So after taking AB in your tree, you have to take AC in your tree and then go ahead. Is that clear?
Can we do it at once?
Yeah, so see, initially you took the right one, so which is the edge of AB, because it is of the cost minimum overall, right? So what you will do, Prim's algorithm says, first of all, take your root, right? So your root will be this particular AB edge, right? Now what you want to do, you want to grow your tree. So growing your tree means attaching some branches. So attaching some branches means attaching some edges. So what you have to do, you have to attach some edges over this particular tree to get a spanning tree. But when you attach some edges, you have to take care of two things. First thing is it should be of minimum cost, and second thing is it should not create a cycle. So here there are three attachments are possible. You can attach this particular edge AC because A is there in our tree. You can attach an edge BC because B is in our tree. You can attach an edge BE because B is in our tree. So there are three choices or three branches you can attach to your tree. But which you have to select? You have to select the minimum weight branch, right? That means you'll select AC and now you'll grow your tree. Okay. So initially what you did, you select BC, but that's not the correct choice. You don't have to go in an order. So that means you have started with A, then go to B. It's not that like. You have to grow your tree considering the branches. So you have to attach those branches which are of minimum cost and which are not creating a cycle. Okay. Is that clear?
Okay. So after this, we go to AC and CB is not allowed because that will form a cycle.
Correct.
We go to CD.
Right. Correct. CD.
And then we have other two choices. So we can go to either E and F, but since D is the minimum cost
No,
one.
see, here you have so many choices. You cannot attend this edge because it is creating a cycle, but you have this choice, you have this choice, and you have this choice. Now among these three, you have to select the right one. So the right one will be that
B
which is
will be
not
the right.
creating a cycle,
Okay, so
and that
B,
which is
okay.
yeah. So B will fill it. So as you attach B, this choice is now open to you. 7, 6, and 8. So again, you cannot select 6 because it is creating a cycle. So what you will do, you will select 7. Okay, so as you attach this EF edge in your tree, this choice is also there. Now again, you cannot select this one because it is creating a cycle. So what you will do, you will go for next minimum. Okay, you have to go for next minimum. Fine. And now this choice is also there. So among all choices, this 10 one is the minimum. And it is also not creating a cycle. Okay, so this will be your minimum cost spanning tree using Prim's algorithm. But what I'll suggest, Prim's algorithm is little bit picky. So that means at every step you have to take care of those edges which you need to select, you have to consider the choices that if I use this particular edge, how many choices are there to consider. So it's better to use, I think it's better to use Khushkal's algorithm because see, if you apply Khushkal's algorithm here, what you have to do, you have to write down all the vertices at their own places as a disconnected components. So suppose, okay, so A is there, B is there, C is there, and E is there, D is there, F is here, G and H, right? Now what you have to do, you have to attach edges in such a way that it will be of minimum cost and it won't create a cycle. Okay, so among all the edges, the only edge which is of minimum cost is this edge. So you'll select one. Now what is the second minimum cost edge is this edge, right? And it is also not creating a cycle, so I can attach this one too. So you have to attach edges up to that point so that you won't have a disconnected component. So that means you will that all vertices can be reachable from every other vertex. Okay, so this is the second choice. Now this we cannot attach because of the same reason. If we take this edge, we'll create a cycle, right? Another one is the 4, so you can attach 4. Another one is the 5, so you can attach 5 too. Another one is 6, but we cannot attach 6 because if you attach 6, the cycle will be there. The another minimum is 7. Another minimum is 8, but 8 we cannot attach by the same reason. Another minimum is 9, and last minimum is 10. So this will be your graph by Kruskal algorithm. And the cost will be, you can sum it out, 19 and then 30, 35, 37, 38 will be the cost, right? Okay, so I think, in my opinion, Kruskal algorithm are much easier because you just have to throw the edges in such a way that they are of minimum cost and they are not creating cycle until you will join all your vertices. Okay, is that okay? Fine.
Yes,
Ma'am,
ma'am.
this minimum value is the total of all the branches, right? Or is
Yeah, correct.
the
Total of all the branches.
total of, okay.
Just sum
Not
all
the
the branches.
minimum. For example,
No,
if 4 plus 2 is the minimum, so that is not the minimum value. The minimum
no, no,
value
no,
is
no.
total
Sum
sum
of
of
all the, yeah, sum of all the
branches.
branches.
Okay, okay.
But it's the cost of spanning tree. As like
Yeah,
cost of path means sum of all the edges
okay.
used in the path, like that.
Ma'am, when you calculate the 38, then the node H is not covered, am I right?
Which is not covered?
Node H.
All
Vertices
edges?
H. All edges is not connected when you cast 38. You got D, C, A, B, E, F, G, 38, right? So where is H
Yeah.
gone?
Where is what one? F is there, no?
Yeah, in minimum cost spanning tree. So when we calculate the cost, do we have to calculate the every vertices?
No, you don't have to take every edges. We have to take every vertex. That's correct. So all vertices are there: A, B, C, D, E, F, G,
Yeah.
H.
So from F, it's a G and H separate. So
Yeah,
if
but
I
you can start with H. You can go to F and then go to G. There is no direction specified here, right? So you can travel in both directions. So if I want to reach at vertex G, I'll use the vertex F and then go to vertex G.
see, consider from D I went to the till F. From
Yeah.
now, if I go from F to G, then it will be 39. From F to G is 38 and F to H is the 39.
No. So I think, see, this 38 is the sum of all edges. So 1 plus 2 plus 5 plus 4 plus 7 plus 9 plus 10. Sum of all the edges. 1, 2, 4, 5, 7, 10 and 9. So this 9 and 10 will become 19. This 7 and 4 will become 11. So together they will take 30, right? And this 5, 6, 7 and 8. So 38. So the cost of
Okay.
sum of
So all the cost of all the edges we sum up, then it will be 38.
Yeah.
So that will
That
be
is
the
the cost of
minimum
spanning
cost.
tree. Yeah, that will be your minimum cost.
Got the clear. Thank you.
Ma'am,
Okay. Yep.
Ma'am, how to calculate number of possible spanning trees?
Yeah. So
Is
number
there
of possible
for that?
spanning tree differ from graph to graph.
Yeah, is there any shortcut for that?
No, actually, because the closed formula is not there for number of spanning tree. We can tell at max how many spanning tree we can get. That's also difficult formula to prove, but so far we don't have. So far you just have to use your logics that how we can get number of spanning tree. So they will
There
give
is
you only simple graph and you just
yeah.
have to logically answer that. That's all.
There is one question in 11.8.
Okay.
Third question.
How many spanning tree are possible for the graph shown in figure 12.5? Okay, so for this one, you just have to use the logic that how many graphs are there. That's an easy figure. My screen is visible, right?
Yes, ma'am.
So this is 0, 1, 2, 3, 4, 5, 6. So this is our graph and we need to say how many possible spanning trees are there. So there is no closed formula. You just have to use your intuition. So spanning tree means what? That tree inside the graph which is connecting every vertex. Okay. So you don't have to bother about edges. We just have to connect all the vertices and make a tree. Make a tree means we should not create a cycle. Okay. So here in this graph, you can easily observe that if you remove any edge, so suppose I'll remove this edge, then it will break this one cycle. And if I remove this particular edge, then it will break the cycle. So ultimately, the removal of any two edges from these two, what you can say, the squares or tilted, what figure this is? So whatever this is. So if you remove any edges from, yeah, this particular two diamonds, then you will get a spanning tree, right? So one is this spanning tree, 3, 2, right?
It should be
And 4.
16, right?
Yeah, it will be 16. Because here, see, here you have 4 choices to make. You can select any edge and then remove it to break a cycle. And similarly, here you have 4 choices. You can select any edge and remove it. So ultimately, you have 16 choices. So there are 16 spanning tree inside this particular graph. Okay. And the reason is because you just have to break a cycle in this tree. You will get, in this graph to get a spanning tree. Because if you remove more than one edges from this cycle, then you will get a disconnected one, right? Suppose I have removed this one and this one also, then this two is disconnected, but I want a tree, so that means I have to take care of the connectedness, right? So that means you can remove at max, or you have to remove one edges from each of the diamond to get a tree. Okay, and there are 4 choices to make in the first diamond, and there are 4 choices to make in the second diamond. Okay, so let me show you how there are 16 spanning trees. So this is our initial graph. Okay, so suppose I'll choose this, I'll fix this particular edge as a removal from the first diamond, and I'll repeat the edges from there, right? So that means the first one will be this one, 0, 1, 3, 2, and 4, 6, 5. Okay, and this is your first spanning tree. Okay, your second spanning tree will be, I'll fix the removal of the first edge in the first diamond, and I'll rotate these edges. So that means initially I have removed this one. Now I'll remove this 3 to 4 and connect 5, 6 to 4. Okay, this will
Got
be
it,
your second,
ma'am.
right? So in the same circle you can repeat. So ultimately you will
Because
get
there
4
will be some
spanning trees.
shortcut for this.
No, actually there is no shortcut for this.
Okay.
They will give you only simple graph.
Okay, ma'am.
So this one is also
It is not visible again.
yeah, okay,
Ma'am, 11.7, fifth question.
fine. So there is no doubt from practice assignment. Is there any doubt from practice assignment?
No, ma'am.
Okay, no doubts now. Can we go in the reverse order? Is there any doubt from 11.10? Anyone, any doubt from 11.10? There are 4
No, ma'am.
questions regarding trims and coefficients, so I think that will be easy. Yeah, which question from 11.9?
No, 11.7, fifth question.
Okay. So let me ask for 11.9. Is there any doubt from 11.9? Again, there are only 3 questions, so and they are all of minimum cost spanning 3. So I think you guys can answer. 11.8. Any doubt from 11.8? Okay, fine. Let's go to 11.7 then. Which question?
Ma'am, fifth one, last question.
Yeah, so if SPI is equals to SPJ for some J belongs to 0, 1, 2, 5, then which of the following may be the values of I and J? Okay, so here we have computed SP5, SP3 is the graph. The graph is this one.
That means here also we have to compute the values and then check. No shortcut, right?
Yeah, actually, you have to
Okay.
judge what will be the, since the values are up to 2, 3, 4, so we can calculate SP2, SP3, and SP4. There is no shortcut in these questions actually.
Then we can try, ma'am.
Okay. Any other doubt from anyone else? See, graph theory needed a little bit of practice because at this step you don't have the results to directly apply. So you just have to go with your intuitions. Okay, any other doubt from 11.6? So in 11.6 we have solved all the questions. Let's go to 11.5. Any doubt from 11.5? There are only 3 questions and they are related to what things? So, okay, so this is related to actually Descartes' algorithm. So here they have given a certain the other scenario than the burning time. So here at that particular time, that particular city started
Screen
floating.
is not visible.
Yeah, I haven't shared it. Let me see. Okay, so here this is the question. So in the Descartes algorithm, we have talked about the process of burning each vertex, right? So in place of burning, they have written that these vertices actually represent the cities, and there is one flood, and these vertices will or these cities will started flooded at the given particular time. Okay, so that means at time 0 minute, city B was completely flooded. Okay, so in place of burn time they are asking some other time, so you have to interpret in the same way. So ultimately you just have to use the Descartes algorithm here to answer the question. Okay, is that fine? You guys need to solve this question.
Okay, solve it.
Yeah, can we solve? Yeah, we can solve this one.
So we can start with A, right? So we can start with A and then go to either we can go to D.
See, they have mentioned one line that at time 0 minutes, city B was completely flooded in the graph. So that means the source vertex here is the vertex B. Okay, because burning time will be 0 for that vertex. So same thing will happen for this one too.
Okay, so we will start from D and then go to C and then go to
yeah.
E, F.
Let me share my screen. So we'll apply the Descartes algorithm as we already proceeded. So we know that, so let's assume there is some other situation here, but you figure out from the context that, okay, I have to use the Descartes algorithm. Okay. So the Ministry of Earth Science gave flood warning to the cities. There are the cities which are very near to the foothills of Himalayas. At 0 minutes, the city B was completely flooded. So that means at 0, this B was flooded. So in place of flooded, you can assume that at B, the city was burned, right? So in our case, we use the context of burning vertex, right? So in place of burning vertex, here they are saying that they are flooded cities. So that means the flood is increasing in all direction, whatever edges are there. Okay. In the graph, so vertices represent the cities and the edges represents how cities are connected. Okay, so that means the distance between B and C is 1. So obviously the water will reach to the city C much faster than any other cities, right? Because the distance is very minimum. So here we can use the ideology that the flood is increasing in every direction at the same rate. There is no slope or hills or something like that. You can assume that it is increasing it is spreading in every direction with the same rate. Okay. So what does Descartes algorithm say? Suppose you burn this vertex B, then fire will start reaching at every vertex. So at the initial step, the distance of each vertex from the source vertex is infinity. Right. So this is your B. Okay, so this is our vertex B. So initially the distance of B to B is 0 and all other vertex are of infinity distance. Okay, now what happen if the flood starts spreading from the vertex B, it will reach to vertex C first, right? Because it is of the vertex C is very close to the vertex B because of this particular cost. Okay, so here the time will be 1. So that means at 1 minute the city C will be flooded. Okay. Now the flood will start spreading in every direction. So at A, you can reach from B to A by the cost of 4, but you can also reach from B to A by the cost of 3 if you use the circle path, right? So that means the path of vertex, the minimum cost of the path from vertex A to vertex P is via the vertex C. Right? So this cost is now 3. Okay. Now you can go to vertex D, you can go to vertex C, but again the distance is 1. So that's why this city D will be flooded at time 3 plus 1, which is equal to 4. And the city E will be flooded at time 10 plus, wait a minute, I have made a mistake. No, correct. Sorry. 3 plus 1, which is 4, because we are using this circle path. Right. And now 3 plus 10, which is 30. Okay. Is that fine so far? Any doubts? How I am writing these numbers now? Right? Just by the Descartes algorithm, that assume that the flood is spreading in every direction with the same rate. So the flood will started spreading in this direction, flood will start spreading in this direction. But again, since we have reached, okay, so if you use proper Descartes algorithm, this thing won't be there, because at time 4, the flood will only reach up to half of this particular edge, less than half of this particular edge. Okay, so it will start spreading in this direction. So the next city will be burned is city F with a cost 9, and at 9 minutes the flood will reach up to this particular step only, right? And it will start flooding over this direction too, this direction too. Okay, so now 9 plus 4 will be 13. So that means if the flood will reach to the city G by 13 minutes if it follows this particular path. And if it follows this path, this is 10 plus 3, which is 13. 13 plus 1, so that means it will take 14 minutes to flood to reach at G. And if it directly comes, then also 14 minutes. So that means the
From
flooded...
you can go with the 8 minutes, no?
Which
B,
minute?
C, A, F, G.
B,
C,
A,
F, G.
Yeah, A, D, F, G. Correct. So 13 will be the...
AF. No, AF, it can go directly from A to F in
Oh,
one.
yeah, correct. Sorry. Thank you. I missed this one. So you can, from A, you can go to F at 4 only.
Yeah.
Right. So 4 plus 4 will be 8 now.
Even E it goes in 9 minutes for E.
Yeah, for E also it goes as 9 minutes, because I just lost this particular edge. Okay. Any other update? No. Now it's fine, right? Yeah, because of this one, that we can also reach from A to F directly by 4. So as it reached to D, it's also reached to F at the same time. Now from F we can go to G just by count of 4. So it will be there, and then from G we can go to E by 9. Yeah. So this city G will be flooded at time at 8 minutes. So this is our question. So the answer will be the first one, 8 minutes. So at what time will the city G start flooding? So the answer will be 8 minutes. And what is the shortest path to reach city D from the source of flood B? So we have to reach the city D, but we just discovered that we'll start with B, go to C, then go to A, and then go to D. This will be the shortest path of length 4, right? So A to C, and then go to A, and then go to D. So that means this should be your answer, right? So at what time will all the cities will be flooded? So all the cities means at what time? So the city B will be flooded at 0. The city C will be flooded at 1 minute. The city A will be flooded at 2 minutes. So that means you have to choose that vertex which has the maximum flooding time. So that is the city E. So city E will be flooded at time 9. So that means in 9 minutes all the cities will got flooded, right? So here the answer will be 9. Fine. Yeah, so all answers are correct. Is that okay, this question? Any doubts?
Yes.
Any doubts? No? Okay. Now let's go to activity 11.4. So which of the following statement are correct? So what do you guys think, what will be the answer? First one is, if a graph has a negative cycle, shortest path are not defined. A negative cycle is one which has only negative edges weight. In a weighted, okay, so what about first option? Is this option is true or false?
It's true.
True.
It's true, right? What about the second option? A negative cycle is one which has only negative edges weight.
No, you can, the sum of it is negative.
Correct. So that means this is not true. The third one?
Yes,
So in a
it's
weighted graph,
Yeah, that's is true.
it's
uh,
true, right?
here this is 0. So we just
Oh,
in the last session we noticed that
we can have negative one.
yeah. No, in
Yes,
place of
yes,
0 we
only
used
negative.
infinity, right?
But in the adjacency graph, we don't use the infinity, we use the 0, right?
In weighted adjacency graph, adjacency matrix also. Yeah, sorry. In SPN we have used infinity, but in weighted graph we have used 0. So this option will be correct. So as we computed SPN or SP any matrix, there we used infinity if there is no direct connection, or other than we have just used. I actually have doubt over this option. Let's see. Shortest path in a weighted graph need not to be minimum in terms of number of edges. Is what about this option? Is this
Yeah,
correct
it's
or
true.
incorrect?
Correct.
True one. True.
Correct, because need not is given, so it is true.
Yeah.
Yeah, so this all things are correct. Fine. And go to 11.3. So given the following matrix A and B, which of the following represent the product A cross B? So you just have to multiply it. Answer the question 2 and 3 based on the adjacency matrix A or E1 given below. Use the matrix multiplication to find A square. Okay, these things you can just do it, just a computation. Okay. 11.2. So a directed graph and the corresponding adjacency matrix is shown in figure. What are the values of alpha and beta? Okay, so here alpha, directed graph is there. So we know that in adjacency metric of directed graph, we'll write 1 if there is an outgoing edge. So that means if there is an edge from I to I, you will write 1. So there is no edge, so we'll write 0. There is edge from I to J, so that's why we have written 1. There is an edge from I to J. Okay, so you have to consider the orders too. And it's easy to compute alpha, beta. A square also you can compute. Okay, 11.1.
Ma'am, how do we do that? Alpha and beta? Can you get that?
See, so here what is beta? Beta says
K and there should be a connection between K and K.
yeah, but
no,
it is not possible, right?
it's not
Loop is
possible.
not
Yeah,
possible. So beta is 0. And
0.
what about alpha? Is there an edge from K to J? So K to J there is no edge. So 0,
No.
0. Right? So this will be your answer.
Okay. Yeah, understood.
Okay. 11 point. Which of the following question based on the graph below? Okay. So one possible topological order could be this, and the steps are mentioned below along with the longest path computation. Okay. So 0 steps. Okay, so steps are given. You just have to find it out. Which step 3, step 4, steps. Okay. Which of the following is an error in the computational above? Okay, so let's see. So it says that our topological ordering is given. So you start with vertex C. So from vertex C, we will go to vertex E. Okay, so C is of minimum order. So you guys want to solve this question? We can solve it just to topological sorting and longest path problem. So just solve it and then compare it to your table. That will be much easier. Okay, so what about your thoughts? Do you guys want to solve this one?
Yes, ma'am. Can you solve this?
Yeah, we can solve it.
Ma'am, your screen is not visible.
Yeah, I'll share this one second. So this is our topological sorting is already given to us. We just have to monitor the steps. Okay. So in step 1, what will happen? So in step 1, we'll start with the vertex C, because here we will update the in degree of each and every vertex. Okay, so in degree of vertex 3 is 3, in degree of vertex A is 3, in degree of vertex G is 2, in degree of vertex H is 2, in degree of vertex D is 3, F has in degree 1, E has in degree 0, C has in degree 0. Okay, so one possible topological order could be C, E, F, and so on, right? So we have to compute the longest part accordingly. So this is the longest path of the vertex C will be 0, right? So this is C, E, F, B, G, A, H, D. I'm writing in the topological order, but in the option they have written up to A, B, C, D, E, F. So you can compare up, right? And here is your longest path. So we know that longest path of those vertices which has in degree 0 is nothing but 0. That is our convention. So here C and E are those vertices which has in degree 0. So the longest path of these two vertices will be 0. Okay. Now I'll go to those vertices which has in degree more than 0. And then we know the computation that the longest path of those vertices which has in degree greater than 0. So here in degree of vertex J is 0, strictly greater than 0. This is actually equal to the maximum of longest path of all neighbors of J. So there is an H from K to J plus 1, right? So that means suppose this is your vertex J and there are 3 neighbors of this particular J. So that means there are 3 incoming edges to this J from 3 vertices I1, I2, I3. And suppose the longest path of this I1 is 3, longest path of this I2 is 4, longest path of this I3 is 5. So what you'll do, you'll select the maximum one, which is 5, because we are talking about longest path, right? So as the term suggests, longest means max of the thing you have to select. So the maximum is 5, so we'll say 5 plus 1, right? Same type of thing we'll do here to compute the longest path. Okay. So here the longest path of F is what? So where is F? F is here. So there is only one incoming edge and that is from E. So the longest path of the vertex F is the maximum of, since there is only one neighbor of F, so or there is only one incoming edge and that is also from vertex E. So longest path of E and then plus 1. So longest path of E is 0, so 0 plus 1 will be 1. This will be 1. Okay. Now the next vertex is B. So the longest path of B will be, we'll use the same formula. Okay. So the longest path of vertex B is the maximum of its neighbor. So what are the incoming edges of vertex B? It is of from C, from F, and from E. So longest path of C, longest path of F, and longest path from E. And then plus 1. So here longest path of C is 0, longest path of F is 1, longest path of E is 0. So you have to select the maximum one. Maximum is 1. So longest path of B will be 1 plus 1, which is 2. Okay, so the longest path of B is 2. So now what will be the longest path of the vertex G? Okay, so the longest path of vertex G will be, so there are 2 incoming edges. One is from B and another one is from C. So longest path of B, comma longest path of C. And this is the longest path of vertex D. Okay, so the longest path of B is 2, longest path of C is 0. And here we have accounted, right? So these are the longest path. So the maximum is 2, 2 plus 1 will be 3. Right, so the longest path of vertex G is vertex G is 3. I might have written D there, okay. So now the next vertex is vertex A. So there are 3 incoming edges. So we have to select longest path of E, longest path of B, and longest path of G. So this is 0, this is 2, and this is 3. So it's 3 plus 1 will be 4. Okay. And longest path of vertex H will be, so see, for H there are 2 incoming edges. One is from C, one is from G. Longest path of vertex C is 0, longest path of vertex G is 3. So we'll select 3 plus 1 and it will be 4. Similarly for G also, we'll select 4 plus 1 because this H has now longest path as 4. So 4 plus 1 will be 5. Okay, so this will be your longest path computation. So let us see where, is there any doubt in this computation?
No, ma'am.
Okay. So let's see at which step we got this. Okay. So here step 0, its the longest path is initially 0. They have in degree, okay, they mention in degree and then longest path. So it's initial step, okay. So then what they have done, they have also updated the in degree. So this is also you can do. That first node is will remove the chosen one. So we'll remove C, we'll update the in degrees, and we'll update the longest part too. So here they have removed C. So if you removed C, then the in degree of B will change from 3 to 2, and the longest path of B will be 1 because of the same reason, 0 plus 1. The in degree of D will change from 3 to 2, and the longest path will be 1. This is not the correct one because we haven't yeah, that's also correct. Because if you remove C, removal C means removing of all the edges. There are 4 outgoing edges. So 4 entries will get updated. So their in degrees will change from 2 to 1, and the longest path will also change from 2 to 1. Okay, next is removing of E. Yes, so we have to go in topological order, C, E, F, B, G, and then all. So if you remove E, then all the edges which are associated to E will be gone, and the in degrees will also update it. So in degree of A will update to 2, longest path of A will be 1. B will update it to 1, longest path will still remain as 1. C is not there, D is not updated. F is also updated from 0, and the longest path is 1. So this is also correct. Now next we'll remove F. So as you remove F, the in degrees of B and D will change. B and D is changed. This in degree will become 0, this in degree will become 1, longest path will become 2, and here also it become 2. So this step is also correct. Now we will remove B. Do we remove B? Yes, we'll remove B as given in the topological order. So removal of B will change the in degree of A and G and the longest paths too. So here the longest path of B is 2, so longest path of A will become 2 plus 1, that will be 3. Okay, so here we have a problem. That the longest path of A will become 2 plus 3. 2 plus 1, that will be 3. Okay, so as in here also, so as you remember, initially the longest path of B is 0, but as we remove C, the longest path of B will change from 0 to 1. Okay, so here is a mistake. Here we have a mistake in step 4. Longest path of A. Okay. Another one is the longest path of G will be updated from 1 to 3. That's correct because 2 plus 1 will be 3. Okay. Now here, let's see. Here they have removed a wrong vertex. Both they have removed. So that means G and H both they have removed. But we cannot remove both. We can remove only that vertex which are of in degree 0. Okay. What they have done? They have removed G and A, right? So fifth step is they haven't mentioned A here. Okay, A should be here, but it's fine. The in degree of A will not change, so it's safe. Longest path of A will be 4 now because we have removed G. 3 plus 1 will be 4. Are you guys getting what I am seeing here or what I am doing? Hello, am I audible?
Yeah, since you were, yes, ma'am.
Yeah, I'm just checking by the given data, right? How the things
Yeah.
are going.
So
So
in
here
degree
in
as well
yeah,
because the enables are gone, so max changes.
yeah. So in degree changed, but here they have changed the longest part too. So the longest path of H will be 3 plus 1, 4. Okay. Now at the end we have removed H. So as you remove H, the in degree of D will change and the longest path of D will get updated to 4 plus 1, 5. I think there is only error in step 4. Let's see. Yeah, there is only error in step 4. Okay. There are 2 possible topological sorting. That's also correct. But the longest path will be same in both cases. Okay, so this thing you can compute. Okay, is there clear? Any doubt from any other activity? Any doubt from any other activity or any questions?
Can we do one transitive closure of the A cube?
You can do by multiplication, just matrix multiplication.
Okay.
Yeah, that will be much easier. Don't go via the path.
Okay.
And that logical algebra we have, na? 1 into 0, 1 plus 1 is 1.
Okay.
That one. Because if you go via the path, then it's actually difficult.
Yeah, that's very confusing.
Yeah, actually, it's confusing. So that's why I just go with the matrix multiplication.
Okay.
Okay. Any other topic which is not clear from graph theory? We have time, we can discuss it. And about PYQs, so we will have a separate session for PYQ, discussion of PYQs. Because I need to download it from there. So if you have any particular question from PYQ, you can just paste it in the chat, then we can discuss it. That will be better.
I have one. Yeah. So can I paste it here in the chat?
Yeah, you can paste in the Zoom chat. I'll download and then we can discuss it.
Just a minute.
Yeah. Is that issue, that answer sheet response issue is solved or still there? Who was there? Who? Okay, they are not here.
I've shared the link.
Okay. So which question?
Yeah, question number 4 and 6.
So an undirected graph G has 12 edges. Find the number of vertices if the edges of if the degree of each vertex is 2. Is this the question?
Yes, ma'am. Yeah.
Yeah. So here what you have to do, you have to use that relation between the number of edges and the degree of each vertex. Let me share my screen first. So you know that the sum of the degree of each vertex is actually twice the number of edges. This is very well known formula. It's known as a handshaking lemma. Maybe the spellings are different. So it says that sum of degree of vertices is actually twice the number of edges. And the reason behind that this is, see, if you have one edge, then this particular one edge will get will add 1 to the degree of this vertex u, and it will also add 1 to the degree of vertex v. So that means a single edge is contributing to twice in the sum, right? So that's why the sum of the degree of vertices, v, where v belongs to capital V is a set of vertices, this is actually equal to twice the number of edges. Okay, so this particular formula you have to use. And in the question it's given that an undirected graph, and this is true in undirected graph, okay, this is for undirected graph. For directed graph, we have other formula in terms of an in degree and out degree. So in directed graph, we have the formula that sum of in degrees of the vertex v plus sum of the out degree of a vertex v is equal to twice the number of edges. But this is very rare to be appear in our course or somewhere else. But this is very well known and very useful formula, that sum of the degree of vertices twice the number of edges. So here it's given that in an undirected graph, G has 12 edges. So here 2 into 12 is already given to us, that the number of edges is 12. So here I have substituted the number of edges. Find the number of vertices. We need to find the number of vertices. So suppose there are n number of vertices. Suppose n is the number of vertices. It says that if the degree of each vertex in G is 2, so that means we are adding 2 plus 2 plus 2 plus and so on plus 2 up to n times, right? Because we are assuming there are n number of vertices. So since the degree of each vertex is 2, so if there are n vertices, we have to add 2 n times, right? So this is what? This is nothing but 2 into n, which is equal to 2 into 12. We can cancel out 2 and the n is nothing but 12. Okay, so that means the number of vertices is 12. Is that clear?
Okay. And now, yes, ma'am. Yeah.
Yeah. And the next question is?
Question number 6.
6, no? So in an undirected graph, G is given below, and which of the following option is true? The cost of minimum cost spanning tree. Okay, so we have to find the minimum cost spanning tree. Okay, so this is our graph. So I'll use the Kushkal's algorithm, but you can use the Prim's algorithm too.
Kushkal will work better here.
Yeah.
Seems a bit complicated. So
Kushkal's one?
no, I mean using prims would be a bit difficult one here because you have to keep track of lots of things here.
Yeah, correct. Because lots of choices will be there. So we have to select the minimum cost. So again, there are so many ones. So let's take care of ones first. So using this edge, I can join D and E. I can join A and E using the edge 1. I can also join G and F using the edge 1. Because they are not creating a cycle. So it's not, so it won't harm us to attach those edges in our tree, right? So 1 is okay. Now go for 2s. So there are 2 2s there. Any other 2? Yes, this one and this one. Okay, so I can attach these 2 vertices by the H2 and also join these 2 vertices by 2. I cannot join these 2 vertices by 2 because it will create a problem, right? It will create a cycle.
Yes.
But I can join these 2 vertices by 2, right? Now let's go to 3s. So this is the 3. So yes, you can take this as your edge. Another one is this 3. I can take this as 3. Now I don't need more edges because here we got our tree, right? All vertices got connected to each other and that's all. We don't have to take care of all other edges. What will be the cost now? So the cost will be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 plus 6, right? This 3 and this 3. 15. Okay, so the minimum cost of spanning tree will be 15. Is that okay?
Yes, ma'am, it's fine. Yeah, I got it.
Yeah.
Okay. Any doubts in those questions? Okay, fine. So yeah, that's all from my side. If you guys have any questions to ask, we can discuss. Any doubts? If there are no doubts, then we can wind up our session here. We will meet in the next session.
Ma'am,
So you
just
guys, yeah.
sorry, just a question. Can you go to question number 3 at once in the same paper?
Yeah, this question. Which of the following is a not spanning tree? Yes. What is the issue in this question?
Ma'am, I got third option is fine, but when I check with the answer is showing that the first option is also not a spanning tree.
Because the edges are different. See, in the first option, they have connected C and E, but this particular edge is not present in the original graph.
Oh, I see. Okay.
Yeah. So also we cannot assume some edges which are not there in the graph while creating the spanning tree, right?
Okay. Okay.
We have to use those edges which are present in our graph. So what is this site?
Is practice because they have this timed practice questions of all the previous year questions.
Oh. This is not given by the BS team, right?
No, I think some student made this, some senior student made this site.
Nice.
It's pretty good. Yeah. We have all the subjects, I think.
Oh, it is available for all subjects.
Yes, for all subjects, yes. And you have terms till 2022. I think all the papers are available.
Because yeah, here it is easy to spot any paper, but in the dashboard, I think you have to download several PDFs and then check just the
Yes,
difference.
yeah.
Okay. Fine, then see you guys in the next session. Any doubt? If you have, this is the last call. So this will be the last session for, not last, we will have revision sessions, but for week 11, this is the last session.
Just a quick question. So, can you give us an example with the DFS or BFS tree?
Yeah, we can give DFS and BFS tree, na?
Yeah.
So so see, there could be only so from DFS tree you can go to forward edges, backward edges, back edges. Those are questions can be formed. But using BFS, the only questions that can be formed is either spot the BFS tree, or else which of the following edges could be there in the graph or could not be there in the graph. So there are very limited type of questions which can be asked from BFS tree. Okay, but from DFS tree we can ask several type of questions. So yeah,
Yeah, sure.
Yeah, sorry, what?
Yeah, no, you are saying something. Sorry.
No, so that's all. I'm saying that there are only 2 to 3 type of questions which you need to practice.
The other thing is this about the minimum vertex cover. So, can you just go to one of the examples where we had this 16 spanning trees possible,
Yeah.
and try to get the minimum vertex cover of that graph.
Okay, so let's see. So this is again, for finding minimum vertex cover, we don't have formula, so we just have to use our intuition. Okay, so here minimum vertex cover will be 4, as I guess. Yeah. So see what happened. Just make one vertex cover and thought of as minimum. Suppose I'll take the obvious will be I'll take BD and sorry, what is this? A B C D E F G. Okay, so I'll take B, E, D, and G as my vertex cover, right? Because B is covering this edge, right? E is covering these two edges, and D is covering these two edges, and G is covering these two edges.
But we can take O, A, and E.
Yeah, but the number will be same, right? This is C actually. I am made
Okay,
it.
A, C, and F.
Yeah, this is actually they are using 3 vertices only. So see, once you get one vertex cover, now the next thinking will be, is it possible to use lesser than this these vertices? So here the answer is 3, correct. We can use A, we can use C, we can use F, right? If you use A, you will cover these 2 edges. If you use C, you will cover all these 4 edges, and if you use F, you will cover these edges. Okay, so that means we can reduce our vertex cover from 4 to 3. Now the next question is it possible to reduce it further? Okay, so now the answer is, can we get a vertex cover with 2 vertices? So here the answer is no. Why is this so? Because suppose you will use any 2 vertex. So the obvious choice is C. So suppose you will use C. So if you use C, then you can cover only 4 edges, because there is only 4 edges connected to C. Now if you want to take another vertex which will be your vertex cover, and since in the graph how many edges are there, 1 2 3 4, and 4 and 4, 8 edges are there, right? So if you want to make a vertex cover with only 2 vertices, then you need at least another vertex which has degree 4, right? That means which will cover more 4 edges, and it is not possible because every other vertex will have degree 2. So that means we cannot reduce it further. The minimum vertex cover will be of the vertices 3, A, B, C. Okay, so whenever you create a minimum vertex cover, you have to choose those vertices which are of highest degree, right? Because if they are of high degree, it is possible that they will take care of a good number of edges, right? For example, A has degree 2, B has degree 2, D has degree 2, C has degree 4, right? E has degree 2, all other has degree 2. So it is kind of obvious that if we take C in our vertex cover, the C will take care of these 4 edges. Okay, so C will be obvious choice for vertex cover, and then you have to move around that which vertices you can take. Okay, is that fine for you?
Yeah, it's clear now. Yeah, okay.
Okay, any other thing? Okay, any other doubt? Okay, then we'll stop our session here. Thank you guys for joining. See you in the next revision session.
Thank you.
Thank you.
Thank you.